Okay, so we were working on this is the problem we were working on last session. That had to do with quadratic. We were looking at quadratic functions and how to extract some information from the quadratic function and how to be able to graph or sketch the function based on the information we're extracting. And we know quadratic functions have a certain model, which is the ax squared plus bx plus c. And from that, we can extract the roots. The roots are going to be the intercepts in x. And by making x 0, we can find the intercept in y. And looking at the sign of a, we know if the parabola is going to be facing upwards or downwards. So with that information, we can sketch the graph of the parabola. We were missing one thing just to kind of make this graph or sketch as a bit more complete. Does somebody remember what we were missing there? So we already have the sketch of the graph, and that's relatively complete. But there's one thing we could include to make it even more precise. Well, no, not necessarily the range and the domain. The range, in this case, remember that the domain is going to be all of the real numbers. The domain, we can see that the graph is going to be from some certain point in negative y up to infinite. But if we look at that graph that we have there, that we sketched, the point that the lowest point that's along the axis of symmetry, that point, the lowest point or the highest point, depending on how we're looking at the parabola, has a name. It's called the vertex. Okay, so we're missing the vertex. Now, the sketch of the graph, that's fine. But if we wanted it to be even more precise, we could find the vertex, that lowest point in this case. Now, how do we find the vertex? Okay, so let's do the following. Let me choose the color here. Let's do a procedure here to find the vertex. Now, what I'm going to do now has to do with math that you should have already, again, this is math, this isn't new math for you guys. This is math that you should have seen since secondary school, okay? I'm going to say it in English. In English, it sounds weird, but you're probably going to remember it when I say it in Spanish. We need to do a procedure here that's called completing the perfect trinomial. Remember that? Completar el trinomio cuadrado perfecto, okay? Which is completing the perfect trinomial. It's a procedure where we convert part of a polynomial that's of second degree into what's called a perfect polynomial, which is x plus or minus something elevated to the square. We need to do that procedure to find the vertex. So what we're going to do is the following. I'm going to take the original function, which is x squared. Well, before that, to find the vertex, we need to represent the expression. We need to represent the function this way. F of x has to be x minus h elevated to the square plus k. Okay? That's the way we need to represent the polynomial. Somehow we need to turn that, which is the one we have, into this. And the vertex is going to be h comma k. Okay, that's going to be the vertex. So somehow we need to turn the original expression into that. How do we do that? We're going to do the completing the perfect polynomial procedure. So we're going to grab the original expression, x squared minus 2x minus 3. That's f of x. And to do the procedure, does somebody remember what we do in that procedure to complete the perfect trinomial? Let's refresh our math memories. And by the way, remember that when I give you a procedure, which is step 1, step 2, step 3, step up to the dance floor. You don't know that reference. So laugh later. I'm giving you the steps. So you follow the steps when you do the exercise. So there's a reason for me giving you a procedure A, B, and C. Okay. So what I've noticed when you do the workshops or do the homework tasks, then you start doing a certain things. And in some cases, you've gone to do something that the problem isn't asking you to do. So that's the reason I'm giving you the steps, and we're recording this so you can remember the steps. So completing the perfect trinomial is actually very easy. The first thing we need to verify to do that. A, which is the value that's multiplying the x squared, has to be 1 somehow, which is the case right now. So there's not a problem there. Step 2, we're going to grab the number. We are going to grab the number that's multiplying the x. We're going to grab that number. We're going to divide it by 2, and we're going to elevate it to the square. Yes.
We always going to divide the number by 2.
Yes. Yes. It's not the procedure is you're going to grab the number that's multiplying the x. We're going to divide it by 2 always, and then we're going to elevate it to the square. This. If I grab the 2 divided by 2 and elevate it to the square, what do I get? A 1. Okay. Now the next step is that number that I obtained, I'm going to add it and subtract it to the function. Now by adding and subtracting, it means I'm doing nothing to the function. I'm not affecting it. Okay. So the next step is change colors here. The next step is going to be f of x equals x squared minus 2x minus 3, and I'm going to add and subtract the 1.
So the value given, we will take it and subtract from the B and C.
Yes. Actually, no, so I'm going to repeat what Leo asked so everybody can hear it at home. So what Leo asked is, okay, so you add it in B and you subtract it in C. Yes, that's a way of looking at it. Or you could just simply add it and subtract it at the end. Okay, I'm just doing it this way so we can kind of visualize what we're getting at. Yes, please.
Do we also take the value as an absolute value? For example, in this case, 2 was minus 2, but you take it as 2.
Oh, that's a good question, Luis. Okay, we're going to take the value that's being multiplied by the x. Yes, we're going to use the absolute value. We don't care about the sign because it's going to be elevated to the square, so it's going to turn positive anyway. But it's a good observation. It doesn't matter if it's a minus 2 or a plus 2. We're going to grab the 2. We're going to grab the absolute value. Okay, that's a correct observation. So after we do this, what are we going to get here? We have just converted that part of the equation into a perfect trinomial. And so that means that this x squared minus 2x plus 1 is the same as having x minus 1 elevated to the square. And minus 3 minus 1, what does this give me? Minus 4. So that means that the vertex is in what value? The vertex then is
minus 1. -4.
Okay? This is a bit tricky.
Plus,
Yeah, this is a bit tricky because of how the model is represented. Notice that the model says x minus h. So if it's minus already, I'm going to take the h, which is the value. So if it says x minus 1, what is the value of h? It's 1, not minus 1, okay?
you always try to turn it positive.
Excuse me?
You have to only make it positive.
You have to grab the number that's here. So if it's x minus 1, it means x minus h, you grab the 1. If it would have been x plus 1, it has to be the negative.
Because you multiply with the minus x and the equation, right?
Exactly. Now, something similar happens to the -4. The model or the expression says plus k. So we're going to grab the value that's here with the sign. So if it's -4, then here we're going to have -4. Okay, so that means that the vertex is in 1 and -4. So we're going to redraw this parabola. Why? Because originally when we drew it, we didn't mark that part correctly. So we're going to redraw that. Before I do that, questions with this part of the procedure? Leo.
I got lost in the third part where it says x squared minus 2x plus 1 is 3 minus.
Okay, this part here. So are we okay up to this part where we added and subtracted the 1? Okay, so when you add this number to the polynomial, you get what's called a perfect trinomial. A perfect trinomial is going to be x, this sign that you have here, and this value that you have here elevated to the square. That's what's called a perfect trinomial. Excuse me?
It's the root from the third value.
It's the root, exactly. And that's why it's called a perfect trinomial, because always when you have x squared minus bx plus, I'm sorry, b divided by 2 elevated to the second power, you're always going to get x minus that value elevated to the square. That's why it's called a perfect trinomial. And then the other value that you subtracted here, you just add these two and you're going to get in this case, the value of k.
Okay, so you said like you let's say
If you want to say it in Spanish, and we can translate it.
o sea, como por ejemplo, separó toda la función, la separó en partes, o sea, las primeras tres, como que se convirtió en una nueva.
Yes. So what Leo is saying is correct. Once we add and subtract the 1, we have 2 parts. The trinomial, which is the first part, and that's going to be the perfect trinomial. And then there's always going to be a constant.
Entonces, como si el -4 fuera el y-intercept, ¿no?
It's actually not going to be the y-intercept.
No, el shift, ¿no?
It would be the shift, correct. That's a good observation. This formula, this representation, the x minus h squared plus k, it's like we converted the function into a shift left and shift up or down. Well, I'm sorry, shift right or left and up or down. The h is going to be the horizontal shift. The k is going to be the vertical shift. Okay, that's another way of looking at it. Okay. Questions with this before we move on? Give me just less than a minute to do some editing here. Just quick editing here. Sketch. Yes, go ahead.
Once we do the thing, like dividing by 2 and to the square to b,
Mhm.
does the positive value always have to be the one next to it?
Yes, that's a good question. So when we get the number that we obtain dividing by 2 and elevating to the square, that number is going to, the positive version of that number is going to be incorporated into the trinomial. Okay, and the negative one is going to be to the constant. Okay, and so now let's do let's call it a better sketch of the graph.
Teacher,
Yes, go ahead. Please go ahead.
I have a question.
Yes, go ahead.
Why at the end in the H and K it's not -1 and why is not -1? Because
The model we're using, Joel, is this one here. And in that model, the value of H is going to be the negative value that's inside the parenthesis square. So if we have X -1, it's going to be directly the 1. If we would have had X plus 1, it's going to be the negative value of that. It would have been -1. But it's going to be the negative value of, I'm sorry, it's going to be the value of the negative constant that we have inside here. And so since it's already negative, that's why we grab the 1.
So it's like if you're like you have the negative, then take parentheses, then the negative and 1 is parentheses, no? Inside the original.
Mhm.
It is like that, no? That's why you got the positive 1.
Yeah. So in this case, for example, if we would have had, let's say a generic one, X plus 2 squared -5. What is the vertex in this case? The vertex is going to be -2, comma, -5.
Also, you got the opposite of what it's inside in the H.
Yeah, so in the model, it has to be negative. So if it's negative, you're going to grab that value. If it's positive, you're going to have the opposite. Or to see it another way, it's the value, another way of seeing it, which might be simpler, it's the value that makes this 0. So what value makes X plus 2 0? -2. What value makes X -1 0? 1. It's another way of looking at it. It's the value that makes it 0. And it has to be the opposing value of the one you have there. Okay, so now let's try to do a better sketch of the graph. So let's locate the points that we have been talking about. So say 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 4. And let's locate these coordinates. So the intercepts, we had the intercepts in -1 and 3. So we had an intercept here in -1 and another one here in 3. Those are the x-intercept. We had a y-intercept in -3 here. And the vertex is going to be in -4, comma 1. So this is going to be another point. Okay, so this is going to be a sketch of the graph that's a little bit more precise. It's going to be a little bit more spiky than the other one. The 1 -4, this point here is the vertex, okay, which is the lowest point in the graph, okay? The other graph we had was very similar to that one, but we didn't have that section. Let me make this part a little less pointy. A little less point, and that would be the parabola. So, and again, this is a sketch of the graph, but it's a sketch of the graph that's a bit more precise because we have all of those points located. Okay. In the next homework task, there's going to be a bunch of exercises similar to this one. Okay. Questions with this one before we move on to the next section? Okay. 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 Now we're going to talk about our next topic, which are called piecewise functions. Piecewise function. Now, what is a piecewise function? It's kind of like the name indicates, piece. These are functions that are defined in sections. Okay, so the other functions that we've seen up to this point, the power functions, the linear functions, the quadratic functions, these are what we would call continuous functions. So let's say they begin in infinite or in whatever point the domain defines, and they go towards the other extreme of the other point of the domain. In the case, and they're all defined by one mathematical expression. In the case of a piecewise function, it's going to be a function that it's actually going to be comprised of many functions, and each function is going to have a section to it. So how are these functions defined? They're defined as f of x, and then we usually have an open bracket there. And we have the different functions, and we have the part of the domain that these functions are defined. And so let's look at this piecewise function that we have there. And let's see how we could graph that piecewise function. First thing we need to identify, how many sections does that piecewise function have? It's got 3. Okay. So somehow the graph is going to have 3 sections. So let's look at each of these sections. So we're going to do the graph. I'm going to do each of the sections in a different color. Okay. Fernanda, give me a color of those that you would like to use for the first one. Green. Light green, normal green, or dark green? Light green, good. We're going to do the first one. This first one is going to be with light green. And the first section says that f of x is equal to -1 when x is less than 0. X is less than 0 means that it's going to be 1 for -infinite to 0. And the value is -1. So we're going to mark the -1 here. And this is a constant. So how do we graph a constant? What is the graph of a constant? It's just a horizontal line. Remember that the graph of a constant is a horizontal line. And so this is going to be a horizontal line. Whoops, let's try to make it a straight horizontal line that goes from -infinite to 1. But I'm going to ask you guys a question. When I get to 0, is the value for 0 included or not included, according to the range that I just established there? It's not included because it says less than 0, not less than or equal. And so in a piecewise function, what we do is that we're going to mark that with a little open circle.
But
Mhm.
so what this means, what that means, the x.
We haven't got,
It's not a piece of.
yeah, we're going to get to each section. But for the first section, it's less than 0. So that means that the 0 isn't included. So we're going to mark it with a little open circle. An open circle means that that point isn't included as a part of the function.
Okay, you mark it as a parenthesis as well. It's more useful though.
Yeah, in the case of the graphs, and I'm just using this nomenclature because that's the one you're going to see in the literature. You mark it with a 0. The parenthesis can be a little bit confusing. Okay, it can be not a 0, a circle. It might sometimes be marked as 2 open parentheses, but usually the circle is easier to identify. Okay, let's see. Marco, give me a color of the ones that are there that is not green. blue, light blue, normal blue, or dark blue? Light blue. Okay, so light blue is gonna be this one. Now, this says that the function is gonna have a value of x when x equals 0. That's kind of like a that's kind of like a riddle. It's gonna be x when x equals 0, only when x equals 0. So when x equals 0, I'm gonna have x, and so if x equals 0, what is the value of x? That's kind of like a riddle there. If the value is gonna be x and for x equals 0, then what is the only value I'm gonna have of x for this section? 0. So the next part of the graph is going to be 0, 0, which is gonna be this point here. Now notice that I am putting a circle here, but I'm filling in the circle. Filling in the circle means that that point is included as part of the domain, is included as a part of the function. So basically what this means up to this point is the following. The function is -1 from infinite to 0. And when I get to 0, it stops. And then it continues up here with this point, and next up with the third graph. Let's see. The first Luis who answers, give me a color. We got beat over here, right? And that's the only red that we've got. We don't have tone, so it's gonna be red. We're gonna mark this one as red. And this means that the function is gonna be x plus 1 when x is larger than 0. X being larger than 0 means from 0 to infinite without including the 0. Now, I'm gonna do this in sections, okay? The graph for x plus 1, I hope everybody identifies that it's the line. It's a line that's been shifted up 1 unit. It's x plus 1. Remember the shifts and so x plus 1 means that I've got the line, which is x, and that has been shifted 1 unit up to this point here. And we're going to have that. However, according to the domain here, is the point here that we have for x equals 0 included or not included as a part of the function? It's not included because it's an open interval. It says larger than 0, not larger than or equal. So that means that this point is going to be an open point. Okay. And that's a piecewise function. It's a function that's divided in sections. This same function could have been written as follows. There's two, there's another way in which we could have represented exactly the same function if we, well, no, actually, this is the way we could represent it. To be x for x equals 0. Okay. Just on those 3 sections. Okay. So always when we have a piecewise function, we're going to analyze each of the sections and imagine you're graphing just that section in that range. Okay. And then you kind of put them all together. Okay. Questions with this one? Leo. Oh, okay. So let's remember a little bit about the power functions. So first off, the function that we have is f of x equals x plus 1. Okay. So what is the base function here? Remember in the other exercises we did, it's x. And remember that when we're drawing a line, x is a line. But when we're drawing a line, the line is going to go this way. Because the value that we have multiplying the x for the slope is positive. If we would have had, f of x equals minus x plus 1, then it would have been like this. Okay. So questions with this one? Screenshot of this. Okay, questions? Okay. Now, the absolute value of a function. Now, we've already talked about absolute value. We've already talked about the absolute value a little bit when we were talking about inequalities. Now let's look at the absolute value as a part of a function, and what that does to the function and what that does to the graph of it. That's actually very simple. What if I have a function and then I apply an absolute value to that function? What's going to happen is that anything that's negative, it's going to be cut off and flipped over to the positive side. Okay, because remember that the absolute value of something is going to be always the positive value of that something. Okay, so for example, if I have f of x equals the absolute value of x, the graph of that would be this one that we have here. Now, how do we get to that? Well, first, let's look at the base function. The base function would be f of x equals x. Would be f of x equals x. F of x equals x is going to be a line. Draw that with a different color. Yes. F of x is going to be equal to x, and that is a line. We know that f of x equals x is a line. That's the red one that I'm drawing. Now, what happens when I add the absolute value? What happens when I add the absolute value is that anything that's below the x-axis is going to turn positive. It's going to flip. And so that means that the new function is going to be, the positive part stays exactly the same, and the negative part is going to flip over to the positive side of the y-axis. So basically this part is eliminated and it's flipped over to the positive side. And that would be f of x equals x. And if we were to represent this as a piecewise function, it means that whenever x is less than 0, I'm multiplying the x by -1. Whenever the x is larger than or equal than 0, I'm leaving the x as it is. Now, let's try to do the two graphs that are there on the bottom. Graph y equals the absolute value of -3x plus 2, and the absolute value of x squared plus 2x plus 3. Let's try to do those. Let's try to do those, and I'm going to give you a couple of minutes to try to do them in your notes, and then we're going to do them here. Okay, let's try to do these two graphs and see what we get at. And basically with these exercises, it's interesting because these two exercises are going to help us practice everything we've seen up to this point having to do with graphs. So I'm gonna clear these drawings. I'm gonna jump over here to the whiteboard. Okay, and so we're gonna have, I think it's called example 4. And we have to graph f of x equals the absolute value of 3x minus 2. Is that correct? This is 3 negative. No, minus 3x plus 2.
It's still the same.
Yeah, yeah. Kind of, yeah, because we've got the absolute value there, minus 2x plus 2. Okay, so what we're going to do there first, we're going to forget about the absolute value for a bit. We're just going to grab the function that's here. We're just going to look at this one for a moment, which is minus 3x plus 2. And let's graph that before anything else. I'm going to write that down with a different color. So let's graph that before anything else. So we're going to take the minus 3x plus 2. And so let's remember a little bit about our graphing, okay? So first off, we're going to have a minus 3x, okay? Now, minus 3x, first off, we know that x is a line, okay? Let's do this step by step. Just so we can practice, and it's recorded so you have it there. So first is the x. I'm gonna do this with colors. The graph of the x is a line. Do you guys agree with that? I'm gonna be going through the steps, and then you guys tell me if you have any questions. Then we have the x multiplied by 3. What does multiplying by a number do to the graph? Anybody remember that? It's going to stretch it, meaning it's going to put it a little bit closer to the y. So that means that it's going to do this. Okay? I'm doing the different sections in different colors. Then, yes.
How do you go straight like this?
For the value that's multiplying is larger than 1. If it's larger than 1, it's going to get closer to the y. If it's between 0 and 1, meaning if it were 0.3, that would make it flat. Okay. Now let's use another color. Let's use a blue. Then we've got the minus. What is the minus going to do? Literally, what's positive is going to turn negative. What's negative is going to turn positive. It's going to flip, but it's going to flip around the x-axis. So what's going to happen is this. It's going to flip. Okay. We okay up to that point? And then we use green now. Then we've got the +2. What is the +2 going to do? It's not going to stretch. It's going to shift. It's going to shift in what direction? No. Remember, when we're talking about shifts, we're saying up, down, left, or right. Up 2 units. Okay, so it's going to be shifted up 1, 2 units, and so now this means that it's going like this. Now, can somebody tell me what this value is here? where it crosses the, how could we find the x-intercept? So how do we find the x-intercept? Well, remember that the x-intercept is the value that makes the function 0. So if I have minus 3x plus 2 equals 0, this means that minus 3x equals minus 2, x equals minus 2 divided by 3, x equals minus 2 divided by minus 3, x equals 2/3. This would be the x-intercept, which would be here in 2/3. Okay, so I'm going to draw that over here on this side again in green. So the graph of what's inside the absolute value is going to be 1, 2, 1, 2, and 2/3 is roughly around here. And so the graph would be something like this. That line, that squiggly line, see if I can make it a little bit better. That squiggly line that we have there really disoriented today with the extension. Sorry about that. Be a line that crosses those 2 points. Okay. Okay, so that is the function that's inside the absolute value. So now what happens when I apply the absolute value? When I apply the absolute value, and I'm going to write that down in red. When I apply the absolute value, anything that is positive is going to stay positive, and anything that's negative is going to flip over to be positive. So what's going to happen is that this part of the line here is going to stay as it is. And this part that we had on the bottom is now going to flip over. Okay. So the red graph would be f of x, the complete one with the, would be the complete graph with the, with it flipping over. Yes.
So the line of graph that matters is the green.
Yeah, so we're always going to graph the green one, which is whatever is inside the absolute value. Once we have that graph, the only thing we're going to do is we're going to cut off the negative part and flip it over to the positive.
So what is the importance? What's the importance of the other graph?
Can you say that again, louder?
What's the importance of the other graph? I mean, what's the importance of the graph?
Oh, no, I'm just doing that step by step so you know how we got to the green one. Okay, this is a relatively simple one because it's a line, but we could have a more complex one. And so I'm just going through each of the steps so we can sort of practice and remember the shifts, the reflections, the stretches and the compressions. Okay, let's,
It flips like it goes the other way because of the absolute value, right?
Mhm.
So every time there's an absolute value, what it's gonna shift, it's gonna flip.
it's gonna flip along the x-axis. Okay, so the flip is gonna be along the x-axis and there's gonna be a symmetry in that flip. I want you guys to try to do example number 5 for next class. We're gonna have a workshop next class, but I'm gonna ask you guys to try to do example number 5. Yes, go ahead.
The line will be from, well, it's gonna be like from, I'll say 2 to the 2/3.
Uh-huh.
Only 2. Because I think you can only take the positive 2, place it in the graph, and just find the 2/3. That's the line. So we don't need like the other part, just the positive 2. Well, it's like a, well, I don't know if you can do that or.
So could you repeat? So
Like you can skip all the first part, the negative 3x, and then just take the positive 2. That's your y. And just,
yeah, you can, yes, correct. So again, there's many ways in which we can sketch a graph. So what you're saying, Leo, is also valid. Okay, I'm gonna make the x 0 and I know the y-intercept, which is 2. And if I find the 2/3, that's actually gonna give me the slope and I can graph it that way. That's another way of doing it. That's correct. This is a line, so it's very simple to find the 2 intercepts. We could have a more complex function where we would need a few other things, but yeah, that would also be valid. Again, I did the steps here with the different colors, so just so we could practice the concepts of the shifting, of the compressing, and all that stuff. Okay. Let me jump back to the PowerPoint. And the last topic of this section is called combining and yes.
We go back to example number 5.
Yes. Remember that all of this is in the PowerPoints in Blackboard. So all this information is there. And we're going to see that one at the beginning of next class. Okay. So the last topic of this section is called combining and composition, which is basically what we do when we have 2 or more functions and we're going to do some sort of operation with them that will literally combines them or creates or actually creates a new function based on these individual functions. And so let's assume that f and g are 2 functions. Then we're going to have a series of operations that we can do with f and g. We can add them, we can subtract them, we can multiply them, and we can divide them. And that's literally doing that with the functions. It's literally doing those operations. And then there's another function that's called composition. So assuming that we have f and g are 2 functions, the composition is when we make f a function of g or g a function of x, which kind of means putting one function inside the other. Okay, that's called the composition. The only note there is if we're doing the division, obviously the function we're dividing by should not be 0. So let's look at a few examples of these. Screen. Okay, let's look at some examples here of this. So let's assume that we've got 2 functions. There's a bunch of these exercises in the next homework test. they're relatively simple. They might be a bit laborious depending on how complex the functions are. So example number 3. Let's assume that we've got two functions. F of x equals x squared plus 3x plus 1. We got another function that's called f of x equals 2x plus 1. And we want to find the composition f of g and the composition g of f, which means in the first case, we're making g a function of f. And in the second one, we're making f a function of g, which means in the first case, we're grabbing f and we're putting it inside g. And in the second case, we're grabbing, in the first case, we're grabbing g and putting it inside f. And in the second case, we're grabbing f and putting it inside g. Let's look at that example first, and then we've got another one where we've got two different functions and finding the composition as well. So let's look at the first one. We've got x squared plus 3x plus 1, and g of x is 2x squared plus 1. This is the complete result, but let me do it over here in the whiteboard just so we've got the steps to it. So f of x equals x squared plus 3x plus 1. And g of x is 2 squared plus 1. Two x squared plus 1. And so the first thing we're going to find is f composition of g of x. Okay. And what does that mean? It means we're going to grab g of x and we're going to put it into f of x. So I'm going to do it this way to kind of explain what that means. So if I've got f of x, I'm going to write it down here in a very exaggerated manner. I've got x squared plus 3x plus 1. That's f of x. Now imagine I erase the x's, and instead of the x's, I'm going to substitute g of x. So instead of x squared, I'm going to have whatever g of x is, which is 2x squared plus 1. And instead of the x I had here, I'm going to put 2x squared plus 1. So I'm basically putting g of x inside f of x. Okay.
So teacher, it's like giving the x in f of x the value g of x.
Exactly. We're basically grabbing the value of x for f of x now is going to be g of x. And the rest is just practicing some math here. This is going to be This is going to be 4x to the 4 plus 4x squared plus 1 plus 6x to the squared plus 3 plus 1. And so the complete composition is going to be 4x to the 4 plus 4x squared plus 6x squared is 10x squared. One plus 3 is 4 plus 1 is 5. And then the other combination would be G, the composition of G and F, or G composition of F. And we're gonna do something similar for that. So imagine that we have G. So G is 2x squared plus 1. Imagine I eliminate the x, and instead of the x, I substitute f, which would be x squared plus 3x plus 1. And then we have to expand that polynomial. So I'm going to do it this way. Two, and this is going to be x to the 4. To do this expansion. What I'm going to do is that I'm going to consider this to be 2 blocks. So this is going to be 1 block and this is going to be another one. And so this is going to be the same as having x to the 4 plus 2 times 3x plus 1 plus 3x plus 1 squared plus 1. This is just algebra. G composition of x is going to be then 2x to the 4 plus 6x plus 2 plus 9x squared plus 6x plus 1. Yep, I didn't multiply by the 2 here. Just give me a moment here. I didn't multiply here by. Do this again. 2. All of this is multiplied by 2. I forgot about that. And we're going to verify the signs in a little bit. So Leo, you mentioned something about a sign. So this is going to be x to the 4 plus 6x plus 1 plus 9x squared plus 6x plus 1 and plus 1 here. And then we multiply everything. Yes. This is going to be 2x to the 4. 6x plus 6x is 12x times 2 is going to be 24x. 2 times 9 is going to be 18x squared. 1 plus 1 is 2 times 2 is 4 times 1 is 5. And there's a plus here. Just check if I can make a mistake there. Put an 11 there. Okay.
Oh, teacher.
Let me just check something.
I was going to say it was that in the we have 3x plus 1 plus 3x plus 1. I think that 1 has to be negative, no? So you can it has to cancel.
No, in this case here, it's imagine that you had x plus a elevated to the square. So this would be equal to x squared plus 2ax plus a squared. So if it's positive, everything is going to be positive. If one of the values inside were negative, then that's when it would need to be negative. Let me just check here. Square 2. Oh, wait a minute. Give me a moment here. I was missing here. I'm missing here a value. I'm gonna correct this. I have a mistake here. Okay, give me a moment. So remember that. So this is in the recording, and this is going to be in the final PowerPoint. Okay. So I made a mistake here that I need to correct. So here it's going to be x squared x to the fourth, then it's going to be 2 times x squared times 3x plus 1. So this is going to be 2 times x squared, and the 3x plus 1 elevated to the power of 2. So now let's expand this. This is going to be 2 times x to the 4 plus 2 times 3 is 6x to the 3 plus 2x to the squared times 1 is 2x to the squared plus 9x to the squared plus 6x plus 1 plus 1. Now we can expand and add the common elements. So this is going to be 2x to the 4 plus 12x to the 3 times 2 times 9 is 11 times 2 is 22x to the squared. 2 times 6 is 12x. 2 times 1 is 2 plus 1 is 3. And that would be the complete polynomial. So these composition exercises are a bit tricky. They're a bit tricky. They're not tricky. They may be a bit laborious depending on how complicated the functions are. Take a screenshot of this. Questions with this one?
So the final answer is the bottom.
For g of f, it's the bottom one, and for f of g, it's the one there in the middle. So these would be the.
So can it be like a problem where you said it has to be like g of f plus f or g?
Yeah, there could be a problem where, yeah, I think there's a couple of problems where they're asking you to do a bunch of combinations with with the functions. So, yeah. Mhm. So let me switch over to the PowerPoint. Now, for next class, meaning for Thursday, we're going to have another workshop that has to do with homework task number 8, if I'm not mistaken. Homework task number 8 is already in Blackboard. That's been in Blackboard since last week. Homework task number 8 is for next week. It's not for this week, it's for next week. And remember that next week we're gonna have the workshop with Dr. Shunk on Tuesday and Thursday. So we're not gonna cover new material next week.
Is he coming or are we going to be on Zoom?
No, it's gonna be on Zoom. We're not having our guest professors visit yet. I think that's probably gonna be freed up by next year, hopefully. I'm expecting that the classes next year are gonna be like this, normal. We're gonna have people coming over and things will get back to normal. So this is going to be the workshop for this Thursday, okay? Meaning for next class. Let me send it same dynamic as last time, okay? Okay. I remember that Estrella has tutoring. Let's look at one more exercise here. Just let me, hide the slide. Look at how this composition concept can be applied. So combining composition. Now let's assume that we have a weather balloon. Okay, these balloons that go up to the atmosphere, they can be these sort of satellites that can be used to gather information in the atmosphere. So we've got a weather balloon and it's being inflated with gas. Now, the radius of the balloon.
What's the weather balloon?
Oh, a weather balloon is literally a balloon. So it's literally a balloon that you send up to the atmosphere. Usually what you have in that balloon, you put you put some sort of box or something that has sensors. Okay, so you're sending it up to the atmosphere, and with those sensors, you're measuring things. Okay, you could literally be measuring, I don't know, humidity. You could be measuring mostly humidity, maybe even measuring wind speed. So a weather balloon is literally something that you're going to send up to the atmosphere to get information about the weather. Okay, and so think about this, and think about a normal balloon. You've got a balloon, okay, and that balloon you're inflating. Now, in this case, it's being inflated with gas. And there's a certain rate that the gas is going into the balloon. And that means, and right now it says that it's the radius of the balloon is increasing by 5 centimeters per second. Okay, so the radius of the balloon is increasing. Why? Because there's gas being put into the balloon, and the balloon is getting large. Okay. We want to express the volume of the balloon with regards to the time. So is it clear that the radius of the balloon is increasing and the volume is increasing as well? They're giving us the rate of change of the radius. Now we want to find the rate of change of the volume. Okay, and this is an example as to how the composition can be used to represent these. It's basically, we've got two functions. One is a function that has to do with the volume. Another function has to do with the rate or the velocity of the gas. How do we combine those two to create one function that relates the volume to the rate? I'm sorry, the rate of growth. Okay, so let's walk through this. So first off, let's consider that the balloon is a sphere. Right now, we're not going to necessarily bother with the fact that the balloon might not be a regular object. Let's assume that the balloon is a sphere. So the radius of that balloon is increasing at 5 centimeters per second. So that means that if I want to represent that as a function, it means that the radius of the balloon is a function where this is the constant of the function, which is 5 centimeters per second. Okay, so if we were to represent the rate of change, it would literally be a line. That goes from 0 upwards. And the rate of change is that per 1 second, we've got 5 centimeters. Okay? Is it clear that it's a line? It's a constant.
Yes.
Every second, we have 5 centimeters. So at 1 second, we're gonna have 5 centimeters. At 2 seconds, it's gonna be 10 centimeters, and so on and so forth. It's a constant rate of change, and a constant rate of change is represented by a line. Now, the volume of the sphere, we have a formula for the volume of a sphere. The volume of a sphere is represented with this formula. The volume of a sphere as a function of the radius. Now, before I go to the volume, another thing that's important is that this expression that we have here, r of t equals 5t, is a function. It's the radius as a function of time. That's important because up to this point in math, we're only looking at y equals f of x, and y and x. It's the same thing. It's the same as if I would have given you f of x equals 5x, or y equals 5x. Only difference is that x now represents time and y represents the radius, okay? And so now we have, so this is the same as having y equals f of x equals 5x. And so now the volume of the sphere can be represented as a function as well. So the volume with regards to the radius is going to be 4/3 of pi multiplied by the radius to the third. That's a formula for the radius of a sphere. That's the formula for the volume of the sphere given the radius. So notice something here. Let's say that I call this G. G, but in this case, it isn't G of X, it's G of R is equal to 4/3 pi r to the 3. Okay?
Why does the f of x equals 5x is so y?
In this case, for this representation here, because the dependent variable is always going to be the x, and the independent variable is always going to be the x, and the dependent variable, we call it y. It's the vertical axis.
Okay, so the time is independent.
Uh-huh.
So
Yes.
So it needs to be y equals f(x).
Uh-huh. Yeah. So the time is the independent variable, which would be equivalent to having the x. The radius is the dependent variable, which would be equivalent to the y. And so now imagine that we have g of r. And so actually what I need to get to, or what I'm trying to get to, is a function g that has to do with time. So instead of having r, I'm going to substitute r of t here. And this function that we have here is actually g composition of f. Meaning that I'm grabbing f in this case, which is r of t, and I'm putting it inside the new function. And so now if I do that, I'm going to be able to create a new function. I'm going to be able to create a new function where I'm substituting the radius into the volume function. So I have the composition, in this case, V composition of R, or V, which is the volume, is a function of the radius. So I know that the radius of t is equal to 5t. I grab that and I substitute it here. And now I have a new function, which is the volume as a function of time. So now the volume isn't a function of the radius. The volume is a function of time based on the increment of the radius. So I've created a new function which is the composition of V and R. Okay, so this is one example of an application of the composition, where basically we have two functions and we want to relate them.
Like in physics, when you combine, like in physics, when you combine formulas to make things.
Exactly. So this is an example, like you mentioned, Daniel, like in physics. So we've got the volume, which is a function of the radius. We've got the radius that's increasing with regards to time. Now we're combining those two to find an expression where now the volume increases or is related with regards to time. Okay, questions with this one? Yes. Yes, go ahead, Luis.
In the middle part.
Mhm.
I don't know how you get to that result.
The second one?
Yes.
Okay, so first off, we've got the formula for the volume. The expression for the volume said that the volume with regards to the radius was equal to 4/3 pi multiplied by the radius to the 3. This is the formula for the volume of a sphere with a radius given.
Why to the
That's the formula for the sphere. It's similar. If I were to tell you the area of a circle, we know that the area of a circle is pi times r squared. This is a formula for the volume of a sphere. And so,
is not a substitute.
yeah, so we know that the radius with regards to time is 5t. So we grab this, bring it over here, which is this substitution here, and elevating this to the 3, 5 times 5 times 5 multiplied by 4, we get 500 pi, and t elevated to the 3 is t to the 3. So now this new formula is volume with regards to time. Okay, good.